Okay, and our next speaker I'm pleased to introduce is Sergei Nirenburg of RPI.
All right, good morning. I will be talking on the topic of metacognition for mutual trust. So how can metacognition be used to increase trust in AI systems by the operator is one of the questions, the seed questions for the workshop, and indeed this direction of trust receives the lion's share of attention in most current AI applications. For instance, this is what Christian also talked about a little while ago. So explainability of AI is intended to enhance human users' trust in AI decisions, and trustworthiness of AI emphasizes establishing and maintaining human users' trust. And this issue reflects the perceived need to improve the utility of today's reactive AI agents powered by LLMs. And one problem here is that too many users believe that AI agents are sentient and know what they are doing. And people tend to think that AI systems are smarter than they actually are. And this is a well-known fact going back a phenomenon since the time some of you may still remember Eliza and Perry. I have, in my career, have seen many examples of that. So this is something that was called thin trust by Salins and Kuckelberg. The quote, the definition is, thin trust is not well justified and possibly manipulated, and arises in situations where systems act as if they deserve trust or appear as trustworthy fellow agents. So this may be sufficient for non-critical application areas such as advertisement, education, and entertainment. Education, not so much. It was not listed here, right? So I just misread. Unfortunately, thin trust also facilitates success in some nefarious application areas, from cheating on homework and exams to making gullible humans believe many kinds of disinformation. So the direction of trust in which artificial agents are required to develop, maintain, and adjust trust in human users receives less emphasis. Shallow examples of this AI trust in humans exist. For instance, CAPTCHA is that, right? So this trust is a counterpart of thin trust. The agent does not have any idea about whether the human agent knows what it is doing. But this thin trust suffices for this application. But we need to go toward something that doesn't exist yet completely today, and this is the mutual trust. The long game of AI involves developing AI agents that can be deployed as full-blown members of cooperative human AI teams. This is what many of us, if not all of us, want. And thin trust is not enough for such agents. So we need mutual trust. Okay, so I looked at the Routledge Handbook of Trust and Philosophy, and I found this definition of trust as a five-place relation. A trusts B with X in circumstances C for reasons R. To establish and maintain mutual trust, both A and B must be able to continuously assess and update the competences X, for which A and B can be trusted, the circumstances C in which cooperation occurs, and the reasons R for expecting that the two conditions hold. These assessments and update operations all require metacognitive reasoning. So the agents in a team must be willing and able reliably to explain and communicate to others their competences, reasoning, intentions, and biases, and also interpret competences, reasons, intentions, and biases of other agents. And this presupposes lots of metacognitive abilities, among which are these 5 that I mentioned. Generating verbal and physical actions to realize internal intentions, including that of maintaining and adjusting trust. Interpreting perceptual signals, including speaker meaning in dialogue. Establishing situational and interpersonal context for signals. Understanding other agents' intentions and reasoning. And explaining the signals and the agent's intentions and signaling too. So when we are talking about human AI teams, agents operate with team-wide goal agendas, plans, and actions, optimizing team-wide reference utility. A team will function optimally if all team members, that is, humans and AI agents, trust all the teammates, including self, which is important, to know what what everybody is doing, how they are doing it, and why. And to make this happen, the agents must have all these capabilities of perceiving and interpreting signals from the outside world, make correct choices of what to do and ways of achieving these goals, carry out the tasks actually that they choose to perform, and correctly interpret the operational situation and communications among the team members to dynamically modify intentions and actions. They need to remember past experiences and be able to learn by being taught through language as well as demonstration. Okay? So being realistic, we need to be realistic. Agents are not always capable to carry out the above tasks because they often have insufficient knowledge, insufficient situational awareness, or insufficient skill. By the way, we assume that they all are honest and want to do their tasks diligently. By the way, this all applies to human teams, not just human AI teams. Any team is like that. So an agent must be able to recognize the lacunae and deficiencies in self and others and be prepared to overcome them over time. So we augment the above set of prerequisites for an optimally functioning human AI team by requiring the agents also to be able to continuously assess and adjust their level of trust in their teammates and self with respect to what they are doing, how they are doing it, and why. Also to adapt their decision-making to this state of affair and have the ability to communicate, teach, and learn to attain better understanding skills and explanatory power. And all of this requires metacognitive abilities. Okay, to support metacognition, agents must be endowed with explicit models of self, other agents, and teams. These models include a cognitive and robotic architecture, and it's great that Christian's talk was before me because he showed us the structure of the common model, and what we do, for instance, certainly conforms to that. But what I would like to stress is the thing that cognitive architecture people don't stress, and that is the need for content. The content is, because content is king here. So what we need to have, that's why I have been talking for a long time about content-centric computational cognitive modeling. So we need to have a number of content elements in those memories that are usually shown as parts of cognitive architecture: knowledge of world and language, reasoning algorithms and decision functions, goals, plans, personality traits, individual preferences, physical and mental states, that is emotions, and models of specific situations, and memory of past events, object situations, and physical and mental states. So Gary Marcus said recently something that we kind of have subscribed to for a long time, AI is unlikely to ever be trustworthy if its makers continue to skip the step of having explicit, meaning-based cognitive models of the world. A few examples of mutual trust and metacognition in the AI agent. So an agent's level of knowledge about a task or a domain impacts the need and the complexity level of training or explanation. So imagine an agent MD who decides how to describe the etiology of a disease to a patient, a human patient. It assesses the latter's level of medical knowledge and adapts the presentation accordingly. If during a prior visit the MD already gave the patient an explanation, then the MD will trust the patient to remember its content. Another example related to the economy of effort. When starting a drive, an autonomous vehicle agent will trust the rider teammate to indicate where they are going before coming to a choice point in the road. The agent will not ask about it, not initiate this question until it is approaching a choice point in the road. You see, this is just a simple thing, but this is human behavior too. You see? All right, multitasking. While driving along a route, executing a physical action, an autonomous vehicle agent can maintain a dialogue with the rider, a human team member, on any topic. For instance, noticing road work on a side street, the agent can make a mental note to avoid this street in route calculations, at least for some time span, and also could mention the situation in the dialogue, trusting the rider to avoid it in any route planning as well. Another example about memory and user preferences. Having learned that a trip includes a visit to the pharmacy and picking up a child after school, a trusted autonomous vehicle agent will schedule the latter task first because the child should not be kept waiting. Another example of the same, when teaming with different human teammates, a furniture assembly robot will choose the order of assembly operations that it knows from past experience to be preferred by this particular teammate with whom it is cooperating in this instance of the task. So the trust here is that this teammate is stable in his or her preferences. Okay? Another example, the physical and mental states of an agent impact the choice of goals, plans, and action. An MD, human or agent, will present a choice of treatment plans differently to a patient, agent or human, perceived as either trusting or not trusting the MD. You see, there is this assessment of the interlocutor's trust. Also, the presentation will be adapted to the perceived level of anxiety in the patient. Another example, when direct experience contradicts an opinion or recommendation of a teammate, the agent will lower its trust in that teammate, at least with respect to the issue at hand. For example, when a virtual patient agent's physiological model generates a pain signal during a medical procedure that a human MD had presented as not painful during an earlier visit, the VP, this agent, will lower its trust in this MD, which will lead to a modification of behavior. For instance, at the subsequent visit, it will take the agent longer to agree to a treatment suggested by the MD because it will start asking about alternatives and more explanations and so on. So the above examples are all real. They're not invented. All the above metacognitive capabilities, among many others, have been implemented in a series of proof-of-concept systems at the RPI lab. So all agents in these systems are built on the basis of a version of a cognitive architecture called Onto agent. And for a detailed description of the architecture, the processing modules, the underlying knowledge resources, the particulars of the proof of concept systems, the theoretical methodological basics of our approach to content-centric computational cognitive modeling, and the system development infrastructure, see these books. So Linguistics for the Age of AI has come out in 2021, and it's open access at the MIT Press, so you could just look at it right now. And our next book, called Agents in the Long Game of AI, will come out, we hope, in February, but you know how publishing houses are. I will not be able to discuss a lot from this, so it will be just a few points here and there. So I will try to very briefly present the infrastructure supporting our intentional metacognition capable agents. We call them language endowed intelligent agents, layers. Give just a few illustrations of how metacognition is implemented in our systems, and very briefly introduce this concept of lifelong learning through understanding as a prerequisite for the metacognitive abilities in layer-style agency applications. So the objective is to highlight the importance of metacognition for managing trust, explanation, understanding, interpretation of the world itself, and decision-making capabilities, and to sketch a realistic roadmap for developing layer-like agents, which involves using generative AI and other technological tools. So this is a bare bones view of the on-agent architecture. Not very interesting because it's basic. We have modules for perception recognition separate from perception interpretation. Actually, quite a number of modules subsumed by this big blob, which includes intention, reasoning, and decision making, action specification, and then the effectors. So the perception recognition and effectors are imported. You know, these are commodities, more or less. The largely symbolic part is the central part, and in the perception, interpretation, and action specification, we have a mix of methods. All right, so the main point in this is a little bit more detail about the on-agent, but the main thing, just to show that we rely on really detailed specifications of the content of the long-term memory and the situation model, which is the working memory. This is not to be discussed in detail. It requires more time than just one presentation. But just to stress one point, you see this perception interpretation services step. We are doing three kinds at the moment. Vision interpretation, interoception. You know what interoception is? The signals from the body, pain, for instance. So we have simulated interoception and simulated physiological system for an agent. And language, which is the core of what we used to be doing over the many years. So this is a very diagram which is similar in structure to the previous one, and it just shows how much work there is in just developing interpretation of language into meaning. And this is what we have been doing for a long time, and this is, in some sense, the core of the approach, described in some detail in the book and many publications before it, including prior books. Okay, so proof of concept systems. Oh, I'm doing okay. The first one was the Maryland virtual patient system that uses virtual patient layers, agents, for training MDs and medical students to diagnose and treat the diseases of the esophagus. We worked with a large group of teacher physicians at the University of Maryland School of Medicine for that. So these agents maintain user profiles. Users detect and adapt to agent profiles. VPs mind read users. VPs assess and adjust trust in user, and tutor agent assesses user decisions. So this is a multi-agent system. I don't have enough time to describe all of this, but I have a little bit about it a bit later. So the agents learn new knowledge and use it in subsequent interactions with the MD. And the MD expects the VP to understand more as their interactions continue. Another system was a furniture building robot that learns ontological scripts, complex events through language instructions by a human team member, interpret perception using an ontologically grounded opticon, I mean visual perception, a lexicon for images, and integrate robotic architecture with agent architecture by incorporating links to those hierarchical transition networks or behavior trees in ontologically grounded representations of action meaning. And finally, we also built a simulated self-driving vehicle that learns how to behave in a variety of situations, such as how to get to various locations, how to react to unexpected road hazards, and how to schedule sequences of actions, how to behave in complex situations, such as a four-way stop, what to do at the four-way stop. I will not talk much about the other two, but I will give a few examples of metacognition in the MVP, in the Maryland virtual patient. So an example of opportunistic learning that facilitates trust assessments, an example of trust adjustment due to perception interpretation, example of correct and erroneous mind reading and how it impacts trust, and an example of metacognition regulating the scope of agent processing. So a very brief intro now into the MVP. Why we built it, according to medical educators, medical instruction literature does not provide students with adequate training in cognitive analysis and problem solving for diagnostics and treatment. During their apprenticeship, future MDs typically do not see patients with all the diseases that must be studied, and or a sufficient number of diverse cases of a particular disease. So we have an environment where we have a library. We developed a library of virtual patients. It's in the tens of thousands of instances. And what happens is a particular virtual patient is interacting over time, simulated time. It could be up to 3-4 years with an MD. And also the information could be received and asked for from other medical personnel agents, like radiologists, for instance. And also everything is observed by a tutor. Right, so the virtual patients are double agents. They model both the mind and the body. So the body models, it experiences simulated physical and mental states, such as hunger and fear regulated, experiences physiological and pathological states and processes due to a disease, and responding to external interventions, to drugs, to surgery, but also to lifestyle habits whenever they may happen. So that's the model that we built for physiology. And the agents also are endowed with character traits and personal preferences. The mind model is largely the onto-agent. That's what it is. I will not have the time to describe it in great detail right now. But this is excerpt from an actual interaction between the MD and the virtual patient, and everything in italics is renditions of the agent's reasoning, thoughts. Okay, the rendition in English. I could have shown you the formal structures, but they're really hairy and not interesting. So the MD at some point says, I suggest having an EGD, which is a diagnostic procedure. And the VP says, okay, it doesn't know what a GD is, right? But it recognizes that it's a child of a diagnostic procedure, and also records EGD as a noun in the lexicon, mapping to the ontological concept EGD. So it says, I don't know enough about its properties to agree to having the procedure, because you see the idea is that the patient has to agree to the procedure, and one of the tasks of the MD or MD trainee is to persuade the person to take it. I need questions about risk and pain. So how risky it is? MD, it's not risky at all. It's recorded. Is it painful, only uncomfortable, and so on. And after, there is a function, decision function, about agreeing to certain procedures that contains a large number of parameters, a subset of which would be considered sufficient. Those are all technical details. How things are done is less important. What's important is the content. We need to know risks, we need to know the level of pain and so on, and we have in our development of the systems, we have used a variety of decision approaches. But the main thing is to concentrate on the realistic treatment of parameters of the features. Okay, so this is just a view of what we call under the hood. When the system operates, all of these things are changed and so on. So this is a little bit of the technical side of the presentation. Okay, so the MD agents trust the VP agents to learn and thereafter remember what EGD is. Indeed, the next time the MD offers this particular VP an EGD, by the way, do you know what EGD is? It's the esophagogastroduodenal, you just swallow this awful thing, and they do tests for you. But as always in practice, the abbreviations, acronyms are the rule. So the next time the MD offers this to the same patient, the MD expects the patient to remember what it was and what happened when it was introduced first. So that's also a measure of trust. Reciprocally, the VP trusts the MD to give it correct information to learn. So when simulated EGD turns out to be contrary to the MD's assurances, painful, the VP lowers its trust in the MD's medical knowledge and diagnostic abilities. As a result, during subsequent visits to discuss treatment, the VP, by the way, that's diagnostics, EGD, right? Treatment will be something else. The VP will request more information about available choices of treatment than it would have if it trusted the MD more, okay? So this is just a shallow level of description of what's happening. There is also, the whole process is transparent, could be discussed and shown. Another example, mind reading. In a doctor-patient diagnostic interview, different VP agents respond differently to the MD's question, have you traveled recently? When you are asked, have you traveled recently in the doctor's office, you will assume immediately that the question is about whether you were exposed to some potential risks of catching a disease, right? So this So VPs that are capable of mind reading recognize the goal behind the question and gear their responses so as to satisfy that goal. And VPs that are not equipped with the knowledge and decision functions supporting mind reading respond directly, like the question, have you traveled recently? You see what I mean? So there is a real reason for the question, right? The purpose. But if you don't understand, people understand it. Machines, not always. So Martha Smart says, no, I haven't been anywhere that might have made me sick. And Martha Dumb says, no, I have not traveled recently. Whereas Thomas Dumb, an honest person, says, yes, I traveled by automobile recently. Okay, so there is an issue of the human trusting the agent to have the capability of mind reading, you see. And if we want to build agents that approximate over time human capabilities, it's necessary. Okay, when to stop processing? Actionability-related natural language understanding. This is one of the big topics in our language understanding work. So agent stops processing the moment it understands enough to decide what to do next. This is how we operate. That's why we interrupt people all the time in dialogue. Have you noticed? Well, unless we're very polite. But we understand indeed what's going on, and we can barge in early. So there is horizontal incrementality. Each string ending with a noun, verb, or end of input marker is semantically analyzed. What I mean to say is that, a silly example, a duck was swimming in the water. So if for some reason the fact that it's a duck is salient in the conversation, the interlocutor might, hearer here will stop processing and respond immediately. So this is, if somebody yells fire in room 233, so when you hear fire, you already can do something, you see, you understand. Anyway, more examples could be forthcoming. So on top of that, there is also vertical incrementality. In other words, the stack on the right is the various stages of language analysis for extracting and representing meaning that we have implemented. And in many cases, you don't need to go through the entire depth of the processing because it's resource saving if you don't. And you need to be able to decide to stop processing after any stage. And that happens if the agent determines that it already knows enough of the meaning of the input to decide what to do next. There are practical examples of this too. There are also references for this type of actionability-oriented NLU. So all of this, the decision about how and when to stop processing is pure metacognition, right? Because, and the purpose here is to save effort. Because, the principle of least effort is the main principle that we as humans operate under, right? So laziness is the major engine of progress. Okay, a bit about lifelong learning. A team will function optimally, as I already mentioned, if all team members can do all of those things, and the ninth point here, have the ability to teach and learn, to attain better understanding skills and explanatory power. Yeah, so lifelong learning can be opportunistic, like in the example about the EGD with patient and MD, because the dialogue continued and the agent learned about the EGD as an element of English and as an ontological concept in the background, working in parallel. Or it could be deliberate, triggered when the agent has downtime or when learning is a team-wide goal. So what is learned is the agent ontological model of the world is enhanced and improved. This means event and object types and their properties. Perception side links to the model from language, the lexicon or vision, the opticon, and similar resources for other perception modalities, such as interoception. The action side links between this model and physical action realization in the integrated robotic architecture. So verbal and mental actions do not require additional knowledge support. Because, they are not connected to the physical action by the robot, so they could be processed within the cognitive architecture itself. And also what can be learned is the episodic memory could be enhanced by adding ontological concept instances representing past experiences. So we have tinkered with this learning by reading for a long time, and we had some marginal success with the technologies, the text analytics technologies at the time. This was like 15 years ago and more. And we have actually started to experiment recently with using LLMs for this purpose. The big idea, I didn't show you. So look, the idea is this. So the agent performs regular processing, the analyzer, producing text meaning representation, and feeds whatever the application system is, whatever the reasoning is to occur there. And here you see where I haven't had the opportunity to say that we're devoting quite a lot of effort to having our systems be as fail-safe as possible. So they, in many circumstances, can operate with incomplete understanding. But we want the understanding to be better. So unknown words and word senses, when they are detected in the language analyzers, are sent to the queue for learning. And the idea here is to produce a collection of -1 contexts. If there are musicians in the room, then they will know what a -1 context would be. That is, texts, or let's say sentences for simplicity, where all the words but the word in question are already known to the system. Okay? So they're already in the system's lexicon. And then we analyze all of those and try to, technically speaking, a unidirectional application of selectional restrictions and try to learn the best possible TMRs, and from that also learn the concept properties and so on. There is, you could look at these publications for details. I simply don't have the time. But the idea that I'm trying to mention right now is that instead of all text analytics, we are using now LLMs to get us those -1 contexts. Right. So, by the way, one of the examples of this exercise was reported at that fall symposium that Christian was talking about just an hour ago. Right? The beginnings, but there will be more. All right, so this is a virtuous cycle. The above learning by understanding method is bootstrapped by the currently available ontology of about 9,000 concepts and an English lexicon of about 30,000 word senses. The results of learning augment the agent's knowledge resources and thus continuously improve the quality and coverage both of the routine agent function and of the learning process itself. So we're interested in developing and deploying metacognition-capable agent systems for critical applications, and we must be realists. Human supervision and validation of the results of learning is currently a part of the process, and this is supported also in our environment by all kinds of knowledge engineering methodology approaches and a variety of ergonomic tools. And contrary to popular opinion, this resource acquisition methodology is affordable, especially compared with the overall expense of LLM training. This is from The Economist. So model-related algorithmic and infrastructure work in preparation of LLM-based application takes just 20% of the effort. And all the rest is human toil. Okay? So let's be cognizant of that. Conclusion, doing good. Coming back to a more general kind of view of the field. So at present, most work on trust and explainability is carried out in the framework of generative AI. The research question for that is, how can we make LLMs trustworthy and explanatory? Okay? Which generalizes to the question, what is the maximum utility we can get from LLMs? This is an example of method-driven research and development. Choose a technology and investigate the limits of its utility. It has been with us, this approach, for centuries, right? So it stands as an important approach. But it's limiting from the point of view of working toward the future of the field. And the alternative is a task-driven methodology. That is, you say what it is that we must be able to do, and then you think about what methods you could bring to bear from the methods that you already have, plus the residue is where you have to think hard, as Richard Feynman used to say. You know, you have a problem, you specify it, then you think hard about it, and then you write down the solution. So the long game of AI involves the development of progressively more human-like, social, proactive, intentional, metacognition-capable agents that can trust and be trusted by their teammates in human AI teams. Only such agents can successfully add real value when deployed in critical applications in areas such as defense, healthcare, and others. To facilitate this type of task-driven R&D methodology, one must work on new theories, technology, and methods for developing the functionalities that available technologies and methods cannot support. And this is the methodological credo of our team at the RPI Layer Lab. And one last thing that I want to say is that we do insist of finding ways of using the latest technological advances wherever we see them. But we tend to judge the utility of those tools from the point of view of the needs of getting progress on that goal. And finally, really finally, as you can see, the angle that we have in our work is system building. We want to build systems that do something, even though we understand that as a university lab, we cannot create immediately deployable systems. So we do proof of concept level system building. That's it. Thank you.